At 3:37 a.m. on a Thursday late in the 1980s, one of the largest refineries in the United States was torn apart by an explosion. 8 employees lost their lives, and 18 more were injured. A cloud of toxic chemicals erupted into the air, leading to the evacuation of 4,500 people from the surrounding areas and spreading debris as far as 5 miles or 8 kilometers away. The explosion originated in the refinery's 16-story tall, fluid catalytic cracking unit, also known as a cat cracker. Cat crackers utilize enormous heat and pressure to crack or convert heavy mineral oils into usable products. This particular refinery processed 250,000 barrels, or 10.5 million gallons, of crude oil per day. So, what caused the explosion? The root cause of the explosion was the rupture of a vapor line that led off the cat cracker near its top. In a matter of seconds, the ruptured vapor line released approximately 17,000 pounds, or 7,711 kilograms, of hydrocarbon vapor, which was quickly ignited by the hot operating portions of the cracker, leading to the devastating explosion. The explosion swiftly set the cat cracker and surrounding structures ablaze, creating an inferno that burned through most of the next day. The cat cracker was built in the late 1950s. It was state-of-the-art then and had been maintained in the intervening time. So, what went wrong? Examination of the ruptured vapor line, which was recovered after the incident, showed thinning of the pipe wall from the inside, process corrosion, and from the outside, corrosion under insulation. In summation, corrosion caused the walls of the line to thin until they could no longer withstand the internal pressure and ruptured. How can changes to engineering practices help prevent an incident like this? To begin, let's take a quick look at what enabled corrosion to form. After a thorough investigation, inspectors discovered 4 main factors that led to corrosion of the vapor line. Poor initial design. The location and orientation of the vapor line's elbow created a cup. This cup retained water, one of the key components required for corrosion to form. Limited coating options. Inorganic zinc was used to coat the vapor line, which ceases to protect the underlying metal once all the zinc has been sacrificed. Unfortunately, when the unit was built, lead-based paints had been recently banned, and inorganic zinc was the only low-lead coating suitable for the high temperatures of the unit. Limited insulation options. The block insulation that was used to cover the cat cracker retained and held water against the protective coating. At the time, there were limited insulation options to choose from. Inspection challenges, leading to insufficient inspection. The 16-story catalytic cracker tower had insufficient access and was too hot for inspection while in operation. Previous experience with asbestos insulation and lead coatings also influenced the asset owners to overestimate the service life of this new system. Based on the knowledge and technology of the time, this event was a disaster waiting to happen. In the interceding years, advances in technology and a more thorough understanding have led to inventions. For example, numerous design guides have been created that outline how to design insulation and jacket systems that prevent water from becoming trapped. A range of high-temperature coatings have been developed and a number of insulation materials are available. An immense amount of research had been conducted into the performance of materials, allowing for more accurate service life calculations. And new inspection processes have also been developed, including inspection specialties, such as insulation inspection. As we continue to invest in the corrosion prevention industry, new advancements and developments will emerge, hopefully preventing an incident like this from ever happening again.